All right. In this session, we're going to look at poles, zeros, and systems response. So when we do that, we can look at the time response, and particularly the output of control system is being defined as the system output equals the force response plus the natural response. The force response is the steady state response, or a particular response that we're trying to drive the control system to. And the natural response is also called the transient response or the homogeneous solution. Homogeneous is a mathematical expression, so all of this is founded in mathematical modeling and mathematical systems. So it's what's called the homogeneous or solution. Now, techniques used to determine that system output, we've already explored some of those. You can do it from differential equations, using inverse Laplace transform. Yeah, in some ways that's laborious and time consuming, but it's a valid solution. You can determine the poles and zeros of the system. That's a qualitative description, fast solution, simplifies the evaluation of a system's response. So the poles of a system, of a transfer function in particular, when you're looking at the output of the input, that's what our transfer function is. So it's the values of a transfer function that make the Laplace transform become infinite. And in particular, when we're talking about poles, if you look at your transfer function and look at the denominator, it's any roots of the denominator. The zeros of a transfer function, again, these are the values of the transfer function that make the Laplace transform become zero. So another way to look at zeros is that they're any roots of the numerator. So keep those things in mind. If we deal with a first order system to begin with, and we're going to consider that it doesn't have zeros, and we're going to define the input function as a unit step function. So here's our input of R of S, which is our unit step function. Here's our output C of S, and then our transfer function G of S, which equals A divided by S plus A. We plot that out onto the imaginary plane, and you'll see the value then will be x equals negative A, or sigma equals negative A on that particular axis. Now looking at the transfer function, G of S equals the output over the input, so that's C of S divided by R of S. So our output function, we can rearrange that from our transfer function. So C of S equals RS times our transfer function, G of S value. And then the input function, we said it's a step, unit step, so that's 1 on S. We already know that this is our control function. So using that expression, we can multiply through by that. So therefore, then our output function can be defined as A divided by S into A plus 1. So we take the Laplace transform, or transfer, it doesn't matter, transformation, you end up with your output being as a function of t. It's made up of, as we said beforehand, the forced response and the natural response. So therefore, then when you look up your tables, you'll end up with this particular transform of A divided by S plus A, S times S plus A. You'll end up with the output being 1 minus e to the negative AT. And that defines the time constant which governs the speed of the response of the system. So we plotted that out as a system. We get this characteristic plot. And like all control theory, there are some rules of thumb, and basically this is one of those ones where they start talking about, 63% of the final value at t equals 1 time constant. That's the definition of 1 time constant. And they were rules of thumb made up quite some time ago. And as we say, they're marginal values that enable professionals, technicians, professional people to know how a system operates. So that, if you like, that's the best practice, or that's the rules of thumb that are used by that system. So from the figure, note the significance of the parameter A, which is the only parameter needed to describe that transient response. So that t equals 1 on A. So we evaluate our function at 1 on A, and then we end up with this value of 0.37. If we take that, plug it into our output function, which was 1 minus e to the negative AT, then this is where this 0.63 comes from. So that's a 63% if you look at it in those terms. So that's why 63% equals 1 time constant. All right, so the time constant by definition is equal to 1 on A. The parameter A with the units are per second, because it's 1 over A, is denoted as the exponential frequency. And the time constant is the time taken for e to the negative AT to decay to 37% of its initial value, or another perspective is that it's the time taken for the step response to rise to 63% of its final value. 37 plus 63 gives you 100%. So it's just looking at it from different perspectives. The time constant is also related to the pole of the system, as the pole is positioned at A equals, sigma equals negative A. And so the pole is located at the reciprocal of the time constant. The farther the pole is from the imaginary axis, the faster the response transient response is. The rise time. The rise time is the time taken for the waveform to increase from 0.1 to 0.9, so it's from 10% up to 90% of its final value. And again, that was our output function, C of t equals 1 minus e to the negative at. So if we consider those two particular extremes, the 0.1 and the 0.9, you'll see that we end up with those particular times. So we can find our rise time by finding the difference between them. So rise time by definition is equal to 2.2 over A. Settling time. Again, as I say, these things will become design parameters necessary for your particular control system. You'll need to be within particular settling times, rise times, that type of thing, to make sure that the control system operates appropriately, so therefore it can respond appropriately to whatever your system is. So again, another definition. Settling time is the time taken for the response to reach and stay within 2% of its final value. So C of t equals 0.98 or 98%. So our output function, again, it's going to, again, it's exactly the same expression by using this little first order system. We want the output to be 0.98. So we can do that, go through, do the calculation. So the settling time in this case is equivalent, approximately equivalent to 4 divided by whatever A parameter is. So as we say, there are some little definitions that help us to define particular parameters which will become obviously important when you're analyzing systems and also designing systems. So what about a second order system? Now, a second order system exhibits a wide range of responses that must be analyzed and described for obvious reasons. You want to make sure that your system is robust, your control system is efficient, your control system is able to react in the appropriate amount of time to ensure that you don't get a blowout, a blow up, or whatever the case may be. Now, when varying the response of a first order system, it causes a variance in the speed of the response of the first order system, whereas varying the response of a second order system varies the form of the response of a second order system. Two most important characteristics of second order system are the natural frequency, omega n, which is also called the undamped natural frequency, and it's the frequency of the system without damping occurring, and also the damping ratio, which is constant no matter what the time scale of the response, whether it be milliseconds, years, whatever the case may be. And it's defined, as you can see, the exponential decay frequency divided by the natural frequency, or 1 over 2 pi multiplied by the natural period divided by the exponential time constant. Again, this is the mathematical background. These are the typical forms that we find for a second order system. It'll be more interesting once we start applying these things. So stick with it with regards to the background theory, the mathematical theory, and you'll see once we put it into practice, it becomes much more clear. So the general form of our second order system looks like that as a transfer function. And what we try to do, and you'll find that we spend a lot of time in this initial unit, basically, well, if you like, coming back and modeling using this second order form. You'll see that a lot throughout all the work that we do. So pretty much where you are able to put your poles, you get these different responses. So again, these are characteristic. Here you can see you get undamped when you have your two poles that are on the imaginary axis. You get underdamped response when you have, as you can see, your poles moving around so that they are off the imaginary axis now. They're over on the left-hand plane, left half of that plane. And then likewise, we can move them around when they get very close to each other. You get critically damped, and then ultimately, as you see, overdamped. As I say, these are just characteristic forms. You don't need to remember them. You'll be able to call them out if that's the necessity. But other things, you'll be giving design parameters to maybe make sure that it's underdamped or overdamped or whatever the case may be, or undamped as the case may be as well. No, provide the coefficient of the S squared is 1, then the natural frequency squared can be determined and ultimately the value of the natural frequency. Now, that's very, very important. What you'll find is that when we look at this particular expression, for the transfer function, and when you're doing your problems, get in the habit of making sure that the coefficient, that's what it's really saying, if this is 3s squared plus such and such, simplify this by dividing through by the 3 or whatever coefficient. Make sure that you simplify it before you do anything else to make sure that that's 1. So get into the practice of doing that straight away. That will enable you to read off straight away, as you can see, your natural frequency squared, omega n squared. So once you do that, you'll be able to say, oh, okay, that's omega n squared straight away by looking at the denominator or the characteristic equation of your particular transfer function. So it's a pretty good piece of advice just to pick up right from the start. Now, the rise time, peak time, and settling time provide information regarding the speed of that transient response. This is pertinent as a designer, as they will help determine if the speed of the nature of the response does or does not degrade the performance of the system. And again, all important when you're doing analysis or design, and all important when we start doing some problems. Like all things mathematical, you don't learn by reading about it, you learn by doing it. So the key thing is get in and do the problems, and you'll find that you'll learn and understand much better. Now, the peak time by definition, now I haven't done the derivation of this formula, but please accept this is what it is. And as I say, these are mathematical principles. Basically, we're interested in the mathematical application. The peak time is the time required to reach the first or maximum peak. So TP, the peak time, equals pi divided by omega n, the natural frequency, and the square root of 1 minus the damping ratio squared. The percentage overshoot. The percentage overshoot is the amount of waveform overshoots the steady state and is expressed as a percentage of the steady state value. So there's that formula. Again, it could be a design parameter that you'll need to keep in mind. You might have to do 20% overshoot or something like that, 15% overshoot. Settling time, T of S equals 4 divided by the damping ratio multiplied by the natural frequency. So if you're told a particular value, like this, you might be told the settling time, and you might be told the natural frequency. So you can rearrange that equation to find the damping ratio, that type of thing. So keep that in mind as well. Sometimes you aren't given all the information, you might be given bits of it, so you might have to calculate some particular values. All right, a system response when there are additional poles. Now, the work carried out in the previous section pertained to a system with 1 or 2 poles, because it was a second order system, and that's why it has 1 or 2 poles. Just like you get 1 or 2 roots, yeah? So second order. The formula for the percentage overshoot, the settling time, and the peak time were derived only for a system with 2 complex poles or no zeros. So what happens if we have more than 2 poles, or if there are zeros in actual fact? We can use the formula for percentage overshoot, settling time, and peak time, but under certain conditions, okay? Keep that in mind. So a system with more than 2 poles and with zeros can be approximated to a second order system that has 2 complex dominant poles, so we need to justify that approximation. The formulae for percentage overshoot, settling time, and peak time can be applied to higher order systems by using that location of dominant poles. And that's what I'm saying about we will do higher order systems, but what we will do is we'll approximate them with second order systems, as we do in this introduction unit. Now, dominant pole is usually defined as being a pair of complex conjugate poles which decide the transient response of the system. So what about a 3-pole system that has 2 complex poles and 1 pole on the real axis? So the assumption is that we've got 2 complex poles located at those particular positions related to the damping ratio, the natural frequency. And as you can see, there's a real part, and this is the imaginary part. 1 real pole located at negative alpha r. Now remember, we're going to do the mathematical background, the mathematical design, and what you'll need to do is you'll see when we apply it in the tutorial problems or your assignment or things like that, or in a work example for argument's sake. That's when hopefully it will make more sense to you. So the step response of the system is determined from the partial fraction expansion. So the output of that transform for the C of S, the output function, is going to equal this partial fraction. Or in the time domain, when you go through and actually solve that, you'll find that it has this particular form. So as you can see, it's got sines and cosines, so it's a waveform in nature, like sinusoidal kind of output. Now consider the components of our output for the 3 cases of alpha r. That's our 1 pole located at negative alpha r. So case 1, alpha r equals alpha r1, and is not much larger than the damping ratio multiplied by the natural frequency. So the non-dominant pole is near the dominant second order pair. There are 2 complex poles and 1 real pole. So that basically is the configuration that we're talking about. As I say, these are just mathematical backgrounds, so just bear with it. In the second case, alpha R equals alpha R2, another value, and is much larger than that particular product of the damping ratio and the natural frequency. So the non-dominant pole is far from the dominant second order pair. There's a dominant second pair. There are two complex poles and one real pole. See, it's on the real axis. And then the third case is what if you keep shifting this thing out all the way to infinity. So that's what we've been doing, just shifting it further and further in that left half plane. So the non-dominant pole is located at infinity. That is, it's extremely far from the dominant second order pair. There are your complex. So therefore, then you have that configuration. Thus, the component responses of three-pole systems look like that. Okay, as I say, this is just the mathematical theory, and then what we'll do is start basically applying it. What is the magnitude of the exponential decay? Is it so large that the contributions to the peak time is not negligible? Now, we're able to demonstrate that through a partial fraction expansion that the residue of the third pole, in a three-pole system, with dominant second order poles and no zeros, will actually decrease in magnitude as the third pole is moved further into the left half plane, as we saw. Assuming a step response, then our output function CFS for a three-pole system generally has this form. Okay, so if you multiply through by that S on that denominator there, then you'll see that that's the highest power of S will be S cubed. So that's where the third order comes from. And then as you can see, we split up into partial fractions. Assume that the non-dominant pole is located at -c on the real axis, and that a steady state response approaches unity. Evaluating the constants in the numerator of each terms, you'll end up being able to calculate those from your partial fraction processes. And as the non-dominant pole approaches infinity, or C gets closer and closer to infinity, then what will happen is that you'll see that those values will drop down to be A equal 1, B equal -1, C equal -A, and D equals 0. So D is the residue of the non-dominant pole, and its response becomes 0 as the non-dominant pole approaches infinity. Now, as a consequence, the further the non-dominant pole is positioned in relation to the dominant poles, the better the approximation there is to the second order system. Therefore, non-dominant pole is closer to dominant poles, the poorer the approximation there is to the second order system. And that's really what we're talking about. We're talking about any higher order system, third order, fourth order, fifth order, it doesn't really matter. We're going to be coming back and making an approximation to the second order system so that we can very, very quickly read off values like I was talking about beforehand with the coefficient of the S squared. Always make sure that's 1, then you can straight away figure out what the natural frequency is. That type of thing. System response when there are zeros. Now, it's been shown that zeros of response affect the residue or amplitude of a response component, but do not affect the nature of the response, whether it's exponential, damped, or sinusoidal. So adding a real axis 0 to a two-pole system, again, this is just a random kind of example, but let's just say the poles are located at that two locations, and the 0 location consecutively added zeros are at -3, -5, and -10. So basically, that's the kind of response we get. Note that the response is all very close. Yeah, not much of a variation, to be honest, is it? The outputs, important things to observe are that the closer the 0 is to a dominant pole, the greater its effect on the transient response. And as the 0 moves away from the dominant poles, the response approaches that of the second order system. Using partial fraction expansion in this case, you end up with T of S is approximately equal to A over those two factors, S plus B, multiplied by the other factor, S plus A. Thus, the 0 looks like a simple gain factor and does not change the relative amplitudes of the components of the response. Now, if the 0 is far away from the poles, then A is much greater than B and A is much greater than C. So another way to look at this is that if we let our output function C of S be the response of the system, then T of S with unity in the numerator, adding a 0 to the transfer function yields this kind of form, S plus A multiplied by T of S. Then the Laplace transform the response comes down to looking like this. So where this is the derivative of the original response, and this is, we're scaling it up and multiplying it by the factor of A, so it's scaled of the original response. Okay, now if A, the negative of the 0 is very large, then when we go through the Laplace transform the response, then we end up with just A times C of S, the scaled version. If A is the negative of the 0 is not very large, then when we do the Laplace transform, it has an additional component consisting of the derivative of the response. Now, as it decreases, the derivative term contributes more to the response and has a greater effect. So, for a step response, the derivative is typically positive at the start of the step response, and so for smaller values of our A it's part of the factor, but it's actually a root because the factor is s plus a, so the root will be the a value. So for small values of the root a, you can expect more overshoot in the second order systems because the derivative term will be additive around that first overshoot. All right. Note, if a is negative, placing the 0 in the right half plane, then we end up with this configuration where this is the derivative of the original response, which is typically positively initially, and will be of the opposite one in the second order response term. Now, if we end up with these kind of situations such that that S factor multiplied by our output function CFS is greater than our root times CFS, then the response will initially follow the derivative in the opposite direction from the scaled response. Known as non-minimum phase system, if a motorcycle, a classic example is a motorcycle or an airplane was a non-minimum phase system, then it would initially veer left when commanded to steer right. So as you can see, quite odd situations. The key factor is that really all that's talking about is just saying these are the effects that occur when we try to approximate to a second order system, and the types of things that we can do to enable us to ensure that we get that modeling occurring correctly. Another method is the pole zero cancellation and its effect on ability to make a second order approximation to a system. So here we have this particular transfer function here. If the 0 is located at negative z, the 0 at negative z is very close to the pole at negative 3p. So here's our, remember, we look at the denominator to find our poles, look at the top line to find our zeros, and as you can see, we can pretty much cancel those out. So the key point being that a partial fraction of this particular transfer function will show that the residue of the exponential decay is much smaller than the amplitude of the second order response. All right, so that's again, all mathematical background. When you look at the tutorial problems, it will enable you to test out some of these ideas and some of these parameters about settling time and a whole range of other things. So that's the analog or straightforward continuous version. But also, of course, remember we are looking at discrete or digital processes as well. So we can find poles and zeros in a discrete time control system as well. So as we do that, you can see that if we look at our function here, again, this is the mathematical background. Keep in mind, go through the mathematical background, but the key thing is get in and apply the mathematics. So as I said beforehand, when you do mathematics, the best way to learn mathematics or control systems is to get in and do the problems. And that way, the understanding will come much better than basically looking at the mathematical theory. But in any case, the mathematical theory here talks about that the discrete time transfer function, h of z, is able to be defined as the ratio of the amplitude response, y of z, to the amplitude input, u of z, resulting in that. So that's our transfer function in the digital context. Consequently, the transfer function is an algebraic rational function of the variable h of z. So, factorizing the polynomials in the numerator, n of z, and the denominator d of z, we can turn out and find, of course, here are our factors on the numerator, and as you can see, they will be the zeros, and on the bottom, they'll be our poles. The numerator and denominator polynomials have real coefficients defined by the system's difference equation. By that, and as a result of setting nz equal to 0, it yields the roots, and these are defined as being the zeros. And if we set dz equal to 0, they again, obviously, they're going to yield the roots of the equation, and we call those poles. Note that if we take the limit, as those things tend to, just like with the analog system, we're going to exactly the same thing. As we take the limit for our poles, then overall we'll tend towards infinity. If we take it for our zeros, then as we tend towards that particular value, then our overall transfer function will become 0. Okay, let's look at an example. Determine and plot the poles and zeros of the third order discrete time system with this particular transfer function. So straight away we look at the numerator and denominator, and that will help us find our poles and zeros. So the transfer function can be considered as considering the following form. Again, this is our numerator and z, and our d denominator and z. So the poles of the system are determined by finding the roots of this particular equation. All right, now what I've got a note here. So you should follow, or you should show, demonstrate. So the whole point of the matter is that you're also demonstrating your mathematical prowess and proficiency, and that's exceptionally important because that'll be how I go marking. You just can't suddenly come up with some magical answers. So Engineers Australia is very particular about that. They want you to be able to demonstrate your knowledge. So likewise, when I go to get you to do a problem, when I do the solutions, you'll see a full solution. So likewise, you'll need to go through and demonstrate that you are able to follow mathematical processes and demonstrate your understanding of them. So you should follow full mathematical working for finding the roots of a quadratic in this case. Now for powers greater than that, you can use your calculator or Wolfram Alpha. Indicate what you're using to determine the roots and provide evidence. I've done a full working here as we're lucky. So in other words, when you look at this now, obviously this is not a quadratic. I can't use a quadratic equation or find factors. Sometimes you can factorize things easily. So when you go to find the roots of a cubic equation, you can test. So if I test z equals 1, and we're lucky in this case because the first time we tested is a factor, so z minus 1 is a factor, z equals 1 is a root, but z minus 1 is a factor. So I can do polynomial division, divide through, and then as you can see, I've taken it, my quadratic equation, and I've had it as a first order equation, z minus 1 as a factor, multiplied by this particular quadratic. Now using the quadratic equation, so I've already got one factor, z minus 1, I can use my quadratic equation on the quadratic here and go through and find my second factor. And in this case, as you can see, there are two factors, and an actual factor are complex. So consequently, the factors of my denominator, as a third order, turns out to be 3 factors. So I equate that to 0 if you remember. I'm then able to find the roots of those equations, and the roots of those equations by definition are my poles. Likewise, similar process to find the zeros. Again, it was a third order equation. I go through, in luck, it was 0.5, so the root is 0.5 and the factor is z minus 0.5. So polynomial division, I go through, same thing again. I find that my cubic, higher order, turns out to be 2 factors, a factor of 1 order, and this is 2 order or second order or quadratic. Again, I can find my roots of that particular equation, find the factors and the roots, do that, and likewise, I can equate those to 0, and bingo, they're the zeros of my denominator as well. So there we go. So I've got my poles and my zeros, and we were asked to locate the values for the zeros and the poles, and also to plot them. So the pole 0 plot for the third order discrete time control system with that particular transfer function, then looks like that. So with the zeros and poles is indicated, well, zeros is indicated as zeros and poles as x's, then basically we can plot them out in that way. Now keep that in mind, that's important because then you can see what happens when you shift things around. We talk about dominant pairs and stuff like that. So you can see as you do the analysis, it's exceptionally important, sometimes to plot these things out. So basically that's what we've done. All right, so in this particular session, we've been looking at poles, zeros, and systems response. Yes, there's been some mathematical, expansions and things like that, but don't be too concerned about that. That's the underlying mathematics. Get in and do some problems, and you'll find that the more you apply the mathematics and test out the mathematics, the better you will understand.